Okay, so welcome back, and today we are going to derive the formulas for finding the center of mass, the centroid of a lamina. Okay, so I'm going to take my time with this, so I want you to make sure you pay attention, take notes. A lot of this is going to be very similar to the way we've handled other types of problems involving calculus. We're going to use Riemann sums and take the limit of those sums as n approaches infinity. But before we do that, we're going to take our time and develop the different pieces like we did before in the case of the one-dimensional or two-dimensional. And now we're going to talk about a lamina, and we're going to develop the integrals involved in calculating the centroid of a lamina. Okay, so let me get my markers. So what we're going to do is, again, this is under constant, the assumption of constant density. Okay. So what we're going to do is, again, we're going to take a regular partition of n subintervals, right? So we're assume that we're doing regular subintervals. So we're partitioning the interval from A to B. So here's our A to B, where the interval bounds the region that we're interested in. Okay. Furthermore, we're just going to pick one of those subintervals, x sub I minus 1, x sub I, so that could represent any one of the subintervals. And then we're also going to pick a sample point from this particular subinterval. Okay? Oops. And what we're going to do is use this as a representative subinterval like we have in the past. Now, keep in mind that since we're dealing with a rectangle here, the information from the previous video applies. So remember, where is the centroid of a rectangle? The centroid of a rectangle is right where the midpoint line, right, of the height and the base intersect. So if we take the midpoint of the base and the midpoint of the height, and we take the line, right, the horizontal and vertical lines of those, then where those intersect is going to be the centroid of the rectangle. So that's going to be important in what we're going to be doing here. Okay. So what we're going to do is, in this case, then we're going to define x sub I star as the midpoint of the base, right? So the midpoint of the subinterval. So we're going to do x sub I minus 1 plus x sub I over 2. Okay, so that's where we're going to define. Okay. Now the height of this bar we're going to define as f of x sub I star. Okay, so that's going to be the height of our rectangle. Okay, so right about here. Okay, so let's say our centroid then is located right about here. Okay, where the point is going to be what? It's going to be x sub I star, right? That's the midpoint of the base. And then the midpoint of the height, well, that's going to be what? F of x sub I star divided by 2, right? It's going to be the halfway point from the height. So that's going to be f of x sub I star divided by 2. Okay? So that's going to be important. Okay? So this is our setup. Okay, so let's start by finding the total mass. Okay, or the mass of this one rectangle. Okay, so let's call this m sub I. Okay, so how do we find the mass? Well, just like we did before, we're going to take the area, right? So what's the area of this rectangle? So the area of this rectangle is x sub I star. Oh, I'm sorry. The area is going to be the length of the base times the height, right? So what is this length? Like we did before, it's a regular subinterval. So all of the subintervals are going to be the same. So we could just define the distance here is delta x. So remember, so that's just going to be delta x, okay? And then, just like before, that's going to represent the width of every single triangle or rectangle. Okay, so I think we got all the pieces. So the area of this rectangle is going to be the height times the base, right? So base times height, so that's going to be f of x sub I. Okay, so in this, well, okay, let me step back. So in this case, we're looking for mass. This is going to be area, right? So we need something that's going to cancel the area and give us mass. So that's where the density is going to come in. The fact that we're assuming constant density. Okay. Now later on, we could use we could remove that assumption of constant density and still do this, but we would have to use a density function like we have seen before. But at this point, we're just we're assuming constant density. So rho, remember, represents density. So, and rho is with the units mass per unit area. Okay, so mass per unit area. So if we multiply that density by area, then that's going to give us the mass. So that's what we're going to do. So let's take density. Well, again, constant density. So we're just represented by rho. And then we're going to multiply by that by the mass. So we're going to do density times area right? And so again, this is kilograms per unit area times unit area. And so the areas are going to cancel and we'll end up with kilograms, okay? Which is the mass. Okay, good. So now what is this going to represent? So, well, the density is rho, and the mass, the area is going to be the base times height. So the base times height is f of x sub I star times delta x. Okay, so there's the mass of one of the rectangles. And so of course we're going to estimate m, we're going to take the summation from I equals 1 to n of all of these rectangles. So that's going to be rho times f of x sub I star times delta x. And of course, if we want to get the exact, remember, we can take the limit of this Riemann sum. So again, we're going to take the limit as n approaches infinity of the Riemann sum I equals 1 to n of rho times f of x star delta x. And what happens? Well, we get our integral, right? So the summation symbol becomes the integral symbol. Our limits of integration go from a to b because we're going from this entire interval. And now the rho is a constant, so I'm going to pull that out. And the delta x becomes dx, and the x of I star just becomes x. Okay? So this is going to become rho times the integral from a to b of okay? And so this is what we get for m. Okay, so let me... Okay, so that's our integral for m. Okay, so that's how we derive the total mass, okay, of the lamina. Okay? Now, keep in mind that if we didn't have the assumption of uniform density, then this would not be a constant, and so this would be represented by some density function, and then so we would have to deal with that as well. But we might get to that later. But at this point, this is what we have. And again, so this is the first piece. Okay, now let's do the next piece. So now let's deal with the moments. Okay. So let's deal with the first moment, which is with respect to the x-axis. Okay. So we want the moment of the system with respect to the x-axis. Okay. Now, to do this, we're going to also remember or keep in mind that if we take all of the mass and we apply it to the center of this rectangle, the centroid of this rectangle, that's not going to change the moment of the system. So we're going to assume that everything is a point mass right here. So all of the mass here of the rectangle is centered at the centroid. And we're going to do that for our calculations, knowing that that's not going to change the moment of the system with respect to the x-axis or with respect to the y-axis. So that's going to help us determine how we're going to do this. Okay, so now the moment. Okay, so now we're taking the moment of the system. So remember, the moment of the system is equal to what? The mass times the distance from the x-axis in this case, right? We're doing the moment with respect to the x-axis, so we want to know what the distance is from the x-axis, okay? So let's do that. So what we're going to do is, in order to find the moment of the rectangle with respect to the x-axis, we're going to take the mass, and that's what we just calculated a moment ago, of the rectangle times the distance that the center of the mass is from the x-axis. Okay? So, in this case here, where's the centroid located? Right here at this point, right? So, that's what we're going to use to figure this out. So we're going to take the mass, so the moment m of x, okay? And so let's start with the rectangle, the one rectangle. So if we want the moment of this rectangle, then the moment of the rectangle is going to be the area or the mass of the rectangle, which we already calculated was rho times the area, right? So it's rho times f of x sub I, f of x sub I star times delta x. Okay, so there's the mass, And so now what we're going to do is we're going to take this and we're going to multiply by the distance that the centroid is from the x-axis. Now, so again, we're centering everything here. And so this distance at this point, the centroid, is this distance away from the x-axis. So we're going to multiply by f of x sub I star divided by 2, the halfway point, right? And so if we combine these, what do we get? We get rho f of x sub I star quantity squared delta x, and we get a 1/2. Okay, so that's going to be the moment, right? That's going to be the moment of the one rectangle. Well, we're going to have n rectangles here. So to find the moment of the system, of the lamina, with respect to the x-axis, we're going to sum these up. So that's going to give us our m sub x, right? So is going to be the sum, or approximately, I should say. It's going to be approximately the sum as I goes from 1 to n of this. So it's going to be 1/2 rho times f of x sub I star quantity squared times delta x. And now if we take the integral of this thing, or not, I'm sorry, the limit of this thing, so we have a Riemann sum. So again, we're going to take the constants, pull them out, and so the limit so this equals the limit as n approaches infinity of 1/2 rho times f of x sub I star quantity squared delta x, which then gives us our integral. Oops. The summation. I dropped the summation. So this is going to be the limit of the summation as I approaches 1 to n. There we go. So now that's going to give us our integral. So again, I'm going to pull the constants out. The 1/2 and the rho are going to come out. This becomes my integral. This becomes dx, and x sub I star just becomes x. And so this is going to give me the integral from a to b. I'm going to take 1/2 rho outside. And this gives me f of x squared dx. And that's it. That's our m sub x now. Okay, so that's another piece. Okay? Okay, so now let's do the other moment of the system. So m sub y. Okay, so let's start over. So now m sub y is, again, with respect to the y-axis. Okay, so now we're going to take the centroid from here to here from the y-axis. Okay? Okay. So again, if we focus on the centroid, we want to know, hey, the distance of this thing from the y-axis instead of the x-axis. So the only thing that's going to change is how do we represent the distance of the centroid? Well, now it's the distance from the y-axis. Again, with respect to the y-axis, now we're talking about x. And so the distance is going to be x sub I star. So if we take the same idea, right, the same development, we're going to take the mass times the distance, right? So in this case, what are we going to do? It's going to be, now it's going to be the same thing. So m sub y is now going to equal what? Hold on. It's going to be approximately equal to the sum of the rectangles from I equals 1 to n. Now, watch what happens. So the mass, the area is still the same, right? So it's going to be rho times the area, which we already know. It's going to be f of x sub I. F of x sub I star times delta x. But now what we're going to do is multiply by the distance, right? So this is, we're talking about the moment with respect to y. So we're taking the summation of all of the moments of the rectangles. And for one rectangle, in this case, it's going to be the mass times distance, which now distance is represented by x sub I star. So we're going to take this and multiply by x sub I star. And so what happens? This becomes equal to the limit as n approaches infinity. And now I'm going to rearrange things. So this is going to become the summation as I goes from 1 to n. And now this is going to become rho times x sub I star times f sub x sub I star times delta x. And then of course, we take the limit. Right? And what does the limit do? Well, this is going to change to integral dx. The x sub I stars are just going to become x. And of course, what was the other thing? Oh, and then of course the constant we're going to pull out. So this is actually equal to rho times the integral from a to b of x times f of x dx. And that's our moment of the system with respect to the y-axis. And so there are the three pieces. So basically now we're done. Because now that we can do this, now we can just say we know that the centroid of the lamina is going to be located at x bar equals what? X bar is going to be located at, right, m sub y divided by m, right? So we're going to have the moment of the system with respect to y over m. That's going to give us our x bar. And then y bar is similarly going to be m sub x over m. And so that's where we're going to find the centroid of the lamina. And that's it. So I know I took some time, but I want to make sure you guys understand the development of this for a lamina, because this is going to be important. Okay? So now we're going to do, we're going to introduce the theorem. So now after I've derived this, we're going to introduce the theorem that puts us all together, and then we'll do an example. Okay, see you next time.